value you see there. Green tea consumption was associated with a reduced risk of breast cancer. Okay, so that sounds like we're believing H1. There is an association with lower breast cancer. With a statistically significant test for trend, you can ignore that phrase, that's just a fancy word that says there's an association. And then you see P is less than 0.001. P is less than 0.001. Now, let's remember what that means. We started talking about this last time. Here's a bell curve. Why is there a bell curve there? Did anybody mention a bell curve anywhere in this article? Assume that breast cancer rates are normally distributed. Was that mentioned anywhere in this article? So why the hell is it there? Give me 3 words. That's... Give me 2 more. Central limit theorem. As soon as you start sampling from a population, even at 4 or 5 or 10, bell curves start kicking in. At 1,000, you're definitely going to have one. It's going to be a nice shaped bell curve. This would be what's considered a usual cancer rate for that population. I don't know what the number is. They didn't tell me what the number was in the study, and that's okay. I don't need to know what it is. All I know is there somewhere. Soon, we will attribute numbers to it. I promise. When we start doing the studies, we'll have a value to put in the middle. Generally, do you know what number you usually put in the middle of this curve? I'll give you a good sized hint right now.
50.
0. You put a 0 in the middle. Remember in 243, all that standardization, we would start with a bell curve and then knock it down to a standard normal bell curve. It would have 0 in the middle. You can always just assume 0's there. 0's here. And then you've got standard deviations around that 0. So, here's normal cancer rates. What are these? Austin, what do you call these? Elevated. Elevated. What do you call these?
High.
This is when we go, oh, stop drinking green tea. We think it's making you sick, right? That would be the Mountain Dew curve. Stop drinking Mountain Dew because it's making things worse. So anyway, that's why it says usual or elevated. Now notice what I've called this. I've called this a 95% confidence interval, but a one-sided one. I'm going to take 30 seconds to mention something that I wish statisticians everywhere would do. I wish they would just do these and not do hypothesis testing, which is the back half of our course, is hypothesis testing. Just do one-sided confidence intervals instead of hypothesis tests, because they're essentially the same thing, and you guys already understand ones. You already understand confidence intervals. Confidence intervals give you a low and a high. Boom! You want a one-sided one here, because all you want is a low bound on the cancer rates, and you want to see if green tea pops you outside of that low bound. What is this low bound on the cancer rates? I don't know. I mean, make up numbers. Suppose that they thought the Chinese rate was 18.7 per 100,000 woman years, right? That was that number that was given. Although it's not crucial to have that number, that exact number. So call this 0.01%. Maybe this one is 0.005%, which is lower, yes? What we just learned by simply seeing that P is less than 1 in 1,000 is what happened in the sample data. Where did it show up? Where did it show up?
On the low.
Yeah, way on the low side. Which makes us sit back and go, exactly. That's what it makes us. What number are we looking for as a cutoff? By standard kind of practice, what's the cutoff number? What would this cutoff number, this red area right here would be what?
2.5.
That's by usually standard practice is 5%, yes.
Oh.
So when you get a p-value that comes in below 5%, you go, You don't go, where would be? Maybe here. I mean, that's lower, but it's not significantly lower. Yes, not significantly lower. That's, but when it ends down here, there's one of 2 explanations. What are the 2 explanations? Please, McKenna, give me one.
There's another curve.
I love that. Friend? Hang on. There. Yes, that's what McKenna I just skipped a couple slides. I apologize. McKenna said something very, very wonderful. What you just realized was, if you have data that lands so far to one side of the curve you expect it to land on, there are 2 explanations afoot. Number one is it shouldn't be on that curve. That's one explanation. The one explanation is that maybe it should be on a curve that's got a center that's further to one side than the null curve. I call this the H0 curve, if you will, and I call this the H1 curve. Now the problem is, we know where the H0 curve is because we know what the cancer rates are in the general population. We have a number for that, 18.7 per 100,000 woman years. We don't know where that is. That's why we're studying it, right? We're studying it to try to see where the cancer rates are for green tea drinkers. But if we get data that's so far to the left, it's a pretty good indicator that it's probably on this curve or a curve down here somewhere rather than this curve here. That's one awesome explanation, McKinnon. What's another explanation, which we would call a statistical oopsie? It's an outlier on this curve. In other words, green tea does not affect breast cancer rates at all, and you just happen to draw a sample that made it look like it does. Can that happen?
Yeah.
Of course it can. Of course it can. Every bell curve has outliers. Generally, they're outside of 2 standard deviations. Go ahead, Linda. Say that nice and loud again.
So how do you know if there's another bell curve or it's an outlier or...
Welcome to the back half of this course. You never do. That's why you have to replicate studies whenever possible, to see if the results replicate themselves well. But the problem is, every time you make a conclusion in a statistical study, you could be wrong. So what you try to do is you try to minimize the error that you're wrong at. Carly's already taken us partially down that path by constantly insisting on 99% confidence versus 95% confidence. Do you see how 99% confidence would make the study appear to be stronger? I'm going to back up again if you guys don't mind. This is a 95% one-sided confidence interval, yes? What would a 99% confidence interval look like? What would a 99% interval look like? Where would the cutoff value be? Kevin, go ahead.
It would be tighter.
Tighter what way? Keep going. Actually, it would be further this way. Now here's why. Here's why. Why is this called, you can't really see it, it's down here. Why is this called a 95% confidence interval? Where is 95% in that curve? The gray, bluish gray area is 95%. If we moved it to a 99% interval, how much of the gray area would be shaded? 99%, which means where would this have to go? It would have to come this way a smidge, yes? Exactly how far? Irrelevant. You can look that up on a table. But it would be this way, which means then you'd have to pick up a little more gray in that curve, yes? Now, why would that make... What that essentially would do is it would raise the burden of proof for the researchers. Using an outside term, let's go with you guys. It would raise the burden of proof for the researchers. Would it be harder or easier to show now that green tea is doing something? It would have to be harder, correct? Because the data would have to fall even further to the left. This room right here, think about it this way, and this is crap statistics, but if your data fell here, if it fell here, I keep talking about if it fell here or landed here. We're going to be calculating that starting Thursday, I promise. But it's possible that, say, this guy lands right about here, which is outside the 95% confidence interval, but inside the 99. Which means you could say statistically that you're 95% confident, but not 99% confident. Please never do that. Don't ever find yourself doing that. Again, feel like, well, I'm going to report on this because I can do it. You pick a confidence, you stick with it. If you get results that don't show anything, you get results that don't show anything, you call it good. But that's the idea. With higher confidence, you raise the burden of proof on the test. Now sometimes you don't want to do that. We'll come back to that in a couple weeks. Because you might think, well hell, why not just go for 99.9999999% confidence and raise the burden of proof basically infinitely? And there's a reason for that. It goes back to Linda's question. There's two ways to be wrong. We're only addressing one of them so far. Thank you for that question. It was a great question. It's actually at the heart of what we're doing here. But you got about 3 steps past where I want to be right here today. Because right now, I just want to make sure when you guys see this, you know what that means. That's the big thing right now. So what does that mean again? What does that .001 mean again? Put it in different words. Or put it in words. Or do you guys not like the words? Maybe you don't.